Now we're going to talk about work and energy. Work, we use that term for a lot of different things, and in physics, it has a very specific meaning. It's the quantity that describes the displacement of an object times the force parallel to the displacement. So we multiply the force in newtons times the displacement in meters, and we multiply that times the cosine of the angle between the force and displacement. And just seeing examples of that is going to be helpful. Okay, so when we calculate work, we end up getting a Newton meter. You'll also see us use joules, but it's really better to have a Newton meter when we talk about work. I think the online assessment uses joules, capital J. And 1 Newton meter of work is done when 1 Newton acts on a body moving at a distance of 1 meter. And the SI unit will be a Newton meter for that. So you can calculate work in different ways in terms of the objects that you're looking at. The work can be positive or negative depending on what kind of displacement it has and what direction the force is. And we'll look at some examples of that. So, the direction and the force matter with work. And so, the first example here that we have, no work is done by a force if it causes no displacement. So, I give the example in class. If I'm pushing really, really hard against this wall, exerting a lot of force on this wall, but the wall doesn't move, there's no work. So am I burning calories? Sure, but I'm not doing any work. Forces can do positive, negative, or zero work. And so, if we're pushing a box, let's say, and I'm pushing it to the right, and displacement's to the right, I'm doing positive work. But let's say, there's friction acting back here, and the displacement's to the right. If we talk about the work done by friction, we have a force, right, and then the displacement's to the right, and the angle between those is 180 degrees. So that, if you do that in your calculator, cosine of 180, you're going to get a negative number. So that's actually negative work. The normal force in gravity, if we have the normal force here, force of gravity here, and the displacement's to the right, neither of those are actually doing work because they're both at right angles. And here the person pushing the box is doing positive work because the force is to the right, the displacement's to the right, and friction is doing negative work. It's opposite of the motion, so again 180 degrees there that we have here. So cosine of 0 is 1. Cosine of 90 is 0. So 0 work again with the normal force in gravity, but the person is doing positive work and the friction is doing negative work. Okay, so now we're going to take a look at a situation with a box that's being lifted into the air for 2 meters into the air. So we can draw that out. We have the force applied going upwards, force of gravity going downwards. And if something's being lifted, unless it tells you otherwise, you can assume a constant velocity. And what that means is, the acceleration is the change in velocity over time, right? So if the change in velocity, there's no change, that means the acceleration is 0. So when we set up the forces, it's still important to do the net force and the sum of the forces. We have the positive y up here, negative y down here. So positive force applied plus the negative force of gravity. If the acceleration is 0, then the force of gravity and force applied are equal to each other. And we get the force of gravity, which is weight, which is mg. And we want the force applied because we figure out how much work does he do, how much work does the person do in the box. And so with work, right, is force times displacement times cosine theta. And the question is, what's the angle? It's easy to get this mixed up. If we think about it, the displacement's up, right? In what direction is the force? it's up as well, right? So the angle between those is 0 degrees. And so cosine of 0 degrees is 1, so it's perfect amount of work. So once we find the weight, which is mg, that is the force applied. It's equal to the force applied, we know that. We know how far it goes up, which is 2 meters, and the angle is 0 degrees. So when we place those numbers in there, we get 490 for the force applied, which is also equal to force of gravity as it goes up at a constant velocity. And we can place the values in there. And so we get positive 980 Newton meters of work as the box goes into the air. Okay, so the next one, man holds the 50 kilogram box at arm's length for 2 hours as he stands still. How much work does he do on the box? So if we think about that, you know, holding the box here, and we've got the force applied up, force of gravity down, and we're evaluating the work that's done. So, you know, force applied and force of gravity are balanced, right? So we do have a force, but what do we not have? We have no displacement. So even though this would be, you know, I definitely don't recommend this, holding a box for 2 hours at arm's length, exerting lots of calories, right? But there's no displacement here, no displacement, so there's no work done. And that's important to see. Okay, so the next one, the man's holding that 50 kilogram box at arm's length for 2 hours as he walks 1 kilometer forward. So holding it against gravity here. So yeah, why don't you pause the clip and why don't you think through this and be careful as you do this, and let's see if you can get this. This is a classic work problem example that is important to understand. So pause the clip and see if you can think through this, and then hit play when you're ready. Okay, so the key in this one here, right, the displacement is going like this. So 1 kilometer, you know, 1,000 meters this way. So when we think about work, right, force times displacement times cosine theta, we have the same amount of force, and so we do have that. We do have a displacement, right? Now, what is the angle? The force, right, is, you know, his legs are moving, but the force applied is upwards, right, and the displacement's this way. So what's the angle? The angle is actually 90 degrees. And because of that, cosine of 90 we know is 0, so there's actually no work done. Joules or Newton meters, 0 Newton meters. So that's an important idea to see. And you know, it'll be important to see if what's going on with the angle as you do that. Okay, so now we're going to do an example where we have a lifting situation and we want to figure out the work done. In this case is Jane lifts Tarzan, and then for part B, how much work does gravity do? So in the first one, I want to figure out how much work does Jane do, and then how much work does gravity do. So when we set up our free body diagram, we have our forces, force applied going up, force of gravity going down. Again, we'll assume it's at a constant velocity, so the acceleration is 0. And so yeah, why don't you go ahead and work through both of these. You can pause the clip and then see if you can solve for the work Jane does, and then the work gravity does, and then you can hit play to continue. Okay, so you should, as you set up the forces, you know, the force applied in the y, force of gravity, you know, the force applied would be 686. And then for work, for the first one, it's positive work because the displacement is up, the force applied is up, and the angle is 0 degrees. So the work is positive 6,174. And then the work the work gravity does, if you think about that, right, the displacement is up, the force of gravity is down, the angle between those is 180 degrees, so we'll get negative 6.174 Newton meters. Okay, in this situation we have a box that's being pushed across the floor at a constant velocity, and we can draw a free body diagram being pushed straight across the floor. And there is some friction. We have the coefficient of friction here. We're going at a constant velocity, and we know that the mass of the box here, and we want to figure out how much work does Joe do for pushing 15 meters, and then how much work does friction do. So go ahead and at least get part one and calculate the work that Joe does. Again, you're going to have to set up the sum of the forces in the x and the sum of the forces in the y to do that. And then once you do that, you can solve for how much work Joe does, and then you can check your answer, and then I'll give you a chance to try part two as well. Okay, so you should get, for the normal force, 98 newtons. Force applied and force of friction are equal to each other. There's no net force going at a constant velocity, and the force applied is 49 newtons. And so therefore the work is positive 735 Newton meters, because the displacement's to the right, the force applied's to the right, so the angle is 0 degrees, positive work. Okay, so now what I want you to do is figure out how much work does friction do, so you can pause the clip, and then when you're ready you can check. Okay, so we should get negative 735 Newton meters for how much work friction does. The cosine of 180, the friction's acting opposite of the motion, and so we have the negative work there, and then positive work for the work Joe does.